Okay, here's another example, 17.48. In this reaction, we're told that 2H2S, hydrogen sulfide gas, reacts to produce 2 hydrogens and disulfur gas. We're told that the reaction occurs at 700 degrees Celsius, and we're given a Kc value of 9.3 times 10 to the minus 8. Okay, and then we're told we start with 0.45 moles of H2S in a 3-liter container. And we want to find the equilibrium concentration of H2. So find the concentration of H2 at equilibrium at 700 degrees. Well, fortunately, because if it was anything but 700 degrees, we'd have to do a lot more chemistry to figure that out, and this is okay. First thing to note, you're given a quantity of moles per liter. Well, you might remember that if you take moles and divide by liters, you are going to get molarity, which is the measure of concentration, and fortunately we're given a Kc value. So if I divide 0.45 by 3, I get 0.15 molar. Okay, but we don't know the other two. See? This is what they mean by something called a reaction table. You might have read something about that. What you do then is you make a little matrix, sort of like we did before, where we have concentration in molarity, and then we take each of the species in kind. So in this case, our reaction is going to look like 2 H2S's. I'm not going to write all the little symbols. And then I'm going to have 2 H2s and an S2. Now remember, these are gases, so none of them are going to be 1. If they were solids or liquids, it could in fact be 1. I'm going to write concentration as initial, the change, and then the equilibrium. Okay. So what we know is the initial concentration of H2S is 0.15. We know the initial concentrations of the others are 0. Because we don't start with any. Now, what's the change going to be? So the change we don't know. And anytime we don't know something, we're going to put an X with it, right? So I can see based on the stoichiometry, if I call S2 X, because it's a product, I'm going to get more of it. So I'm going to call that plus X. What about hydrogen? That is also an unknown. But look, if you have an X worth of S2, since this is a 2-to-1 ratio for hydrogen to sulfur, this would be a 2X. And we would form that so it would also be a 2. Where do we get the H2 and the S2? We get them from H2S, so this would be minus some value of X. And because the coefficient is 2, it's minus 2X. Now you see from that little reaction table, we can see that our equilibrium values are going to be 0.15 minus 2x. This is going to be 0 plus 2x, which is 2x, and 0 plus x, which is x. Now we can write an equilibrium expression. Why can we do that? Because we want to find the concentration of H2 at equilibrium. We don't this time want to start with quantities of those necessarily and find a QC. We could find QC to get the net direction of the reaction. But in this case, since we have an equilibrium reaction table, we can just set up the quotient. And so let's do that. Kc would then be products over the reactants. So we're going to have H2 concentration squared because there's 2. S2 concentration as our numerator. And then we're going to have 0.15, H2S squared for our denominator. This will be equal to the equilibrium constant, which is 9.3 times 10 to the minus 8. Okay, we don't know these values, but we have an expression that has things in terms of x, so you would guess that we could substitute and solve, and that's what we're going to do. So we will then substitute in for H2, 2x squared, because that would be the equilibrium concentration. For sulfur, x all over 0.15 minus 2x squared. And that has to equal 9.3 times 10 to the minus 8. Okay, so look what's going to happen. Whatever we get for x, when we solve for it, we can then substitute in here. X will be the concentration of sulfur. Whatever that is, hydrogen will be twice that. And whatever H2S is, it'll be 0.5 minus 2 times that value of x. Okay, here's the tricky part. This would turn into be a quadratic equation. It would. Why? Because you would have to expand this, and you'd have x squareds, x's, and then you'd have a constant value. There is an assumption we can make, and it doesn't always work, but sometimes it does, and you would check it. So if we assume that x is much smaller than 0.15, that means this term effectively becomes 0. If x is a very small number compared to 0.15, 2 times that very small number is going to be a small number. 0.15 minus that small number is going to be very close to 0.15. So again, if you assume that x is much smaller than 0.15, then the denominator becomes 0.15. So this is going to be, if we put it together, 4x squared times x over 0.15 being equal to 9.3 times 10 to the minus 8. Now it's easier to solve. So if I multiply 9.3 to the negative 8 power by 0.15, oops, I'm sorry, I forgot that, didn't I? I got to square it, 0.15 squared. I will get a very small number, 368 and a 2, and then I'll have 4x cubed on the left-hand side. So when I solve for x, it's going to involve a cube root. Remember, that's the same as raising something to the power of 1/4. So if I was to take my point, all those zeros, and divide by 4, I'm going to get 5.23 times 10 to the minus 10. This is a rounded number because my calculator only had so many digits. And I would take this, that's divided by 4, I would take that value and raise it to the power of, 1/3, because that would be a cube root. And when I do that, I get 8.0575 times 10 to the minus 4. And because that's x, that would be molar. So that would be my concentration of S2. But before I can put a fork in it and be done, I have to check my assumption. And the way I check my assumption is I compare it, the concentration of hydrogen, that is, I compare it to my starting value for H2S. Okay, so let me do it this way. I'm going to say that my S2 is going to be 8.0575 times 10 to the minus 4. The hydrogen, if you might remember from the equation, is going to be twice that. So I take that twice. And I get 0.0016 molar. I could find my HI, but that's not what the problem asks me to do. So what I want to do is verify whether or not that's going to be a good number. The way I do this is I compare to the starting value. Okay, listen. That's going to be the value for 2x, right? 2x is going to be 0.0016 molar. I'm going to compare that. I'm going to plug that in as if I was going to be finding the concentration of H2S, and then I'm going to see how much H2S is actually going to be left over. The way I do that is I set this as a ratio to the HI. So here's my check. I take 0.0016 molar, and I compare that as a ratio to my starting concentration of HI, molar. I just divide them. And I get 0.0107. That would be about 1.07%. And the rule is, if this check gives you a quotient of less than 5%, that is less than 0.05, then the assumption is good. We are 95% certain that that's going to be accurate. So in this case, since I came up with 0.0107, that's going to be less than 0.05, which means, guess what? That there's a lot of H2S that's going to be left over at equilibrium. Not much of it is going to break down. And you might see it in the exponent of Kc. That's a small number, not a double-digit number, not a double-digit small number. But that tells us, remember, that the reactant side would be favored. That is, less of the reactant should disappear, and therefore less of the product is going to appear. Use that same strategy when you do number 1749, and that will help.